Basically, we're covering wastewater reuse project. My name is Manuel.
I'm Isaac.
I'm Jordy.
I'm Freddie.
So here's our introduction and problem statement. So basically, we are having a wastewater effluent from Agua Nueva and then transform them into drinking water through the direct potable water reuse system. So there are multiple issues to address here, such as salinity, trace organics, pH, microorganism, and COD, and etc. So for the sake of this project, we are focusing more on the trace organic reduction. So here I'm going to talk a little bit about the trace organic compounds. Basically, they are from industrial, chemical, and pharmaceutical waste. They basically potentially hazardous to human if it ingested. And there are also fluorescent organics pose more potential harm to human. So we're going to cover on the fluorescent organic reduction. So how can the trace organics can be reduced? So basically we are using advanced oxidation process, utilizing the UV and hydrogen peroxide. In here, the picture below, we can see our apparatus. Basically, in the middle, we have a lamp, and then the water running through it with the reaction within the hydrogen peroxide.
All right, so as Manuel said, we're going to focus on fluorescent organic reduction for this part of the direct potable water reuse system. One of the ways to quantify the effectiveness of advanced oxidation in this reduction is shown in this graph right here. Regions 4 and 5 contain more potentially harmful organics. So this is the focus for our reduction, and these values in regions 4 and 5 are taken as an integral. Think of this as a three-dimensional curve where you integrate underneath, and then you can take this value from before and after treatment. This gives you a percent reduction. It's not quantifiable in terms of concentration, but this gives you a picture of how well this system is operating. So our experimental testing, we took Agua Nueva's wastewater effluent. It was treated with ultrafiltration, and this was our feed to the advanced oxidation pilot scale reactor that was shown in the apparatus Manuel discussed. We set a constant residence time of 8 seconds based on individuals who had used this reactor prior. This is the highest residence time in the range they used because we knew trace organics are harder to oxidize. And with this constant residence time, we varied hydrogen peroxide concentration in the feed between 1/4 and around 9 millimolar with the goal of optimizing the peroxide concentration as well as quantifying the effectiveness of the advanced oxidation at reducing these organics. So here are the results. We have percent reduction on the y-axis, peroxide concentration on the x-axis, and you see that it kind of flattens off around 83% reduction at around 3.5 millimolar concentration. This is a sort of limit in terms of how much the system can reduce trace organics overall. So this is going to be our design basis concentration, so we minimize chemical cost while maximizing the reduction potential.
So using experimental results from the AO, we scaled up our design to this process flow diagram, which is divided into 3 main subsections. The first one being the 50% hydrogen peroxide storage tank that will later use its pump to mix with our ultrafiltration filtrate with its corresponding pump. Then all this mixture will run into our scale-up reactors that we decided to use smaller reactors in parallel system. This will later help us have less scale-up variability, where the top 4 pairs will run 24/7, while the ones on the bottom will be used just in case any reactor needs maintenance so we don't have to stop the system at any point. So the design basis for our scale up, based on everything what we said before, we use that 8-second residence time to compensate for that 5 milligallons per day throughput. Our length to diameter in our scale up is identical to to our pilot reactor, where we will use 3.5 millimolar hydrogen peroxide concentration, and the overall parallel system will minimize the length of the reactors. So more reactors will equal less scale-up variability.
Moving forward is the capital cost. So the way we broke this down was the capital cost was based on a 2-year construction assumption. Now this included the price of the equipment, which was determined by scaling up the pilot size and having the same efficiency of 83% reduction in TOC. Another thing that is based on this would also be the chemicals and materials, as well as any kind of construction needed to create the facility to hold the AOP system. The annual operating cost would be broken down into the cost of how much of the chemical was used in an annual basis, as well as the operational cost of how much we would be paying the workers, as well as the maintenance. The total present worth is based on the assumption that how much this part of the facility would, in terms, either net a profit, which by selling the product, or by being able to staying within the permits that are allowed and not having any kind of deviation resulting in fines or any kind of cost that the facility might see. In conclusion, this is a subsection of the total portable reusing system, meaning that this would only be a part of the facility. And as well as this facility, or what we created was to maintain a 5 million gallons a day output with a 83% total organic reduction. Another parameter would be that we would be getting the effluents already going through ultrafiltration, and it's already been treated in that way. So in conclusion, this part of the facility could have a net present worth of about $19.6 million to a company, whether or not they either sell their product or they keep it within the same system and have it be a ways in order for them to save money on fees and other kind of unforeseen circumstances.
Thank you.
Thank
Thank
you.
you for your time. Is that?